can go ahead.
Okay, so I get to go. Would you like to go next, or would you like to
Go right ahead.
Okay. What we know is that Professor Kitcher would like to go last, and that's fine. So, well, I appreciate Dean Moody-Adams introducing the context for this and some of the issues. I'm actually going to take a somewhat different approach. That is, I'm going to talk to science students about what I think you ought to do. This is, after all, sponsored by the Science and Engineers for a Better Society, not the Humanists for Better Understanding of Science. And so I take it that many of you who are here who are scientists are interested in this, and so I'm going to give you some suggestions. I hope this doesn't sound too much like a lecture. I lecture a lot, obviously, so I guess I have a tendency, a proclivity to lecture. But I'm really giving you advice the way I give Sheldon advice as Director of Undergraduate Studies in Chemistry. I give him advice on what courses to take, but I never actually tell him what he has to do. So I want to talk a little bit about what each of us who's a scientist might do to improve the situation. And this is really about taking responsibility for a situation and trying to do something about it without trying to decide who's really at fault, where the fault lies, what the problem is, but just addressing it in whatever way we can. And I think we should each as scientists try to make inroads into this wherever we can. And let me give you an example of that. In general chemistry classes in the fall, we have more than 800 students enrolled in the fall semester. Of that number, 332 are students in Columbia College, the vast majority of whom are not science majors. A very large number are pre-med students, but the vast majority are not science majors, and they're certainly not chemistry majors because we only get a fraction of that number of majors out of any class. In addition, the entire first-year class of the School of Engineering is enrolled. This is a chance, in my view, to make a really big impact on a very large number of students, some of whom are interested in science, some of whom are only mildly interested, and some of whom are just doing this because someone's told them they have to do it. Making inroads, I think, means trying to carve out a space in whatever you're doing to address this problem. So what kinds of things do I think we need to try to do? First, I think we need to try to humanize the endeavor of science. I think there's often, even among scientists, some misconceptions about how science actually has developed, as if certain truths just become revealed and then everyone accepts the truths. There are no real genuine controversies. People just recognize when something right has been done. That is, if you take a class in science, there's a right answer and there's a wrong answer. But science doesn't actually develop that way. And I think one way to humanize it is actually to talk about scientists. In any class you have, any class you teach, any environment you have, talk about scientists. And since thermodynamics is mentioned in this context, I'm going to talk about people who were instrumental in developing the science of thermodynamics in the 19th century. One of the things we can, I think, disabuse ourselves of as well as others is that the truth becomes revealed and we all accept it and that's the way it goes, and there's never a human element to it. It's really not very human, it just happens. But it isn't, I mean, it really developed, as one can see by looking at the history of the development of thermodynamics, in people like Julius Robert Mayer, who was actually a physician. He wasn't a real scientist, he was a physician, who, when sailing with the Navy, noticed something about the color, the depth of the color of blood among the sailors as they went across the equator into the southern hemisphere. He noticed there were changes in the color of the blood. And he, based on this, he figured out very, very important scientific principles having to do with metabolism, and he concluded that heat, by a long series of reasoning, which I'm not going to reproduce here, he concluded that heat and work must be interconvertible, which seems like a trivial thing, but it is the basis of the first law, not the second law, but the first law of thermodynamics. Mayer published an article on this, which was met at best with disinterest and at worst with absolute ridicule. No one accepted what he was saying, in part because he wasn't a member of the right club. Right? He didn't have the right credentials. He was a physician, not a scientist. He had to work extremely hard to get people to listen to what he said. He had to submit this article in 2 different forms to 2 different journals before people actually read it. But even so, he never really received the credit that was really his due for establishing that. Joule later received the credit for establishing the equivalence of heat and work, and he did do really important experiments to establish that. But Mayer made a big contribution too, not as a scientist. He started out as a physician. And he wasn't looking for this. He found it. It was serendipity. And the role of serendipity in science is frequently, I think, underappreciated. I obviously had much too long a presentation. Let me say, the next thing is we need to try to demythologize science. There's this idea that we go and we try to solve a big problem, that we all start out trying to solve this big problem. But frequently things don't work that way. In the field of thermodynamics, Sadi Carnot, who I think you could arguably say started the field of thermodynamics, didn't start out to understand anything scientifically. He started out to solve the problem is, what's the most amount of work you can get out of an engine for a given amount of fuel? It was an economic perspective. How much work can I get for a given amount of fuel? And he wrote a very influential book called Reflections on the Motive Power of Fire and on Machines Fitted to Develop That Power. And it was all about maximizing return on investment, but it established the field of thermodynamics. Later on, much later, although not associated with thermodynamics, Max Planck stumbled upon, in a way, the quantum theory. He didn't set out to discover the quantum theory. Planck had a commission from electric utilities to come up with a more efficient way of lighting. They wanted to get the most light out of a given amount of power. They wanted to get the most economic return. And they hired Planck to consider how light is emitted by filaments and light bulbs. And in the process of considering that, he stumbled upon an observation that led him to the quantum hypothesis. He resisted that hypothesis. He accepted the hypothesis only reluctantly. He didn't say, oh my God, I've discovered something really important, I'm going to be famous. He actually resisted it. He called it an act of desperation done because something had to be done to preserve the physics of the problem. Now, I had my time is up, so I'm not going to go on, but I think the important thing is to connect what we do to other people in a way that they can be engaged in. To see that science is a human endeavor, just as any other endeavor is, and although it has somewhat different rules for processing information, it is a system created by humans, executed by humans, and therefore prone to the same glories and failings that any other human endeavor is. Thank you.